mode.
Hi everyone, thank you for joining us today. My name is Daniel Platt and I will be the moderator for this webinar. I'm excited to be joined today by Zach Norman, a solutions engineer at Harris Corporation. During the presentation today, Zach will discuss how you can get actionable information from UAV and aerial data. If you have any questions at any point during the webinar, feel free to use the questions area of your GoToWebinar dashboard. Zach will try to address as many questions as he can, and if he doesn't get to your question, he will follow up with you. Lastly, a recording of this webinar will be available soon on harrisgeospatial.com. And now I'm going to turn things over to Zach.
Thanks, Dan, and thanks for joining us today. Good morning or good afternoon, depending on where you're at. Like Dan said, I'm going to be talking about how you can get some actionable information from UAV and aerial data. So first, here's my contact information. We're going to do our best to answer all the questions that we can after the webinar. It'll probably be about 10 minutes for the PowerPoint, 20-25 minutes of live demo, and then we'll have time for questions. If we don't get to you today, my email's right there. We'll also be reaching out to people afterwards. So if we don't answer your questions during the webinar, we get a list of all those questions and you should be followed up with. So before we begin with the webinar, I do just want to talk about something very exciting we have going on right now. A couple weeks ago, I gave a related webinar regarding NV1 button. We do have a promotion going on with NV1 button so that you can use it for free until October 31st. There's the URL at the bottom of the screen, just harrisgeospatial.com/one button. It's also the landing page if you go to our website. And there's a little button if you want to get your free trial there. To kind of give you a quick little background on NV1 button, it's a software solution from a business partnership between Icarus and Harris Corporation. And it's basically a software package that's designed to generate georeferenced orthorectified mosaics of UAV or aerial data. And so kind of the point of today is I had a related webinar a couple weeks ago, and today we're going to leave off after you have your orthomosaic. So even if you aren't using NV1 button, you've got Pix4D or Agisoft or some other software package, we're really going to focus on what you can do with those orthomosaics after they've been generated. So to kind of give you a little look at what we're going to talk about today. First, we're going to have an overview of Harris Corporation. We've gone through a lot of name changes throughout the years, and we just went through another one about a year ago. And so we just want to make sure everybody's on the same page with that. Then we're going to talk about the not as exciting stuff, which is getting your data analysis ready, atmospheric correction, Basemap registration. Then we're going to go on to actually some examples of analytics. And after that, we're actually going to do a live demo, and we'll go through most of the analytics that are talked about. So first, Harris Corporation. We're an $8 billion company, 22,000 employees worldwide. There's a lot of engineers and scientists. Because the company's so large, it's split up into 4 different business segments. In our piece, we fit in under the space and intelligence systems. It's basically a lot of sensors. And we fit in geospatial. So in the lower left corner of the screen there, there's a little red box around geospatial. And we're kind of on the analytics side of things. So some of like the software packages that we have or other offerings, if you're not familiar with them, IDL is what we started with. It's the interactive data language. It's a scripting language. You can run all of most of NV's routines and functions through it. It's similar to Python. It's a lot faster. Additionally, we have NV, which is the environment for visualizing images. And I'll talk more about that in just a second. Additionally, we have Jaguar. It's basically a web-based platform for sharing, discovering data, ingesting live video feeds and viewing them live, and really good for distributing information to places where there's low bandwidth. Lastly is Geiger Moonlighter. It's basically a new LiDAR sensor that allows you to collect at higher altitudes while flying faster. So this means that the cost to collect is less so that you can get higher quality data for better price. So kind of to jump right into things, so the majority of what we're going to be talking about today is actually with regards to NV. So first, just to give you a little background on ENVI, there's lots of different analytics for different data types. SAR, LiDAR, if you have multispectral or hyperspectral data, we work well with all of those. We've got lots and lots of supported data types or sensor types, satellites that is, and we pretty much support lots of generic file types as well. So our kind of bread and butter is working with multispectral and hyperspectral images, but we also do a lot of different things as well. So once you actually have that data and have that in ENVI, there's lots of things that you can do with it. This is just a quick little snapshot of stuff. I got this off of our website at harrisgeospatial.com. Change detection, image classification, feature extraction. We also have ENVI in the cloud. It's ENVI Services Engine. We also have IDL in the cloud as well. And so if you want to learn more about that stuff, then you can go take a look at our website. So this is kind of all I have for my summary. We'll jump right into the meat of the webinar today. So getting data analysis ready. So it's not the most exciting stuff, but once you have your orthomosaic, there's really certain steps that you need to do to get your data analysis or ingestion ready. This way, if you go through your data, say you run a Spectral Index or you use Spectral Angle Mapper to find materials in your scene, if you've done the correct pre-processing, then you can actually say with confidence, you can share your results and say, oh, this is the health of these plants, or this is where this material is found in your scene. And so it's really important to follow certain steps. And there's really kind of two things that we're going to be talking about, and that's going to be atmospheric correction and basemap registration. So first is atmospheric correction. The basic idea here is that we've got these two graphics to demonstrate this. So on the left, there's no atmosphere, and there's a little plot for irradiance versus wavelength. Now, irradiance is just the amount of light per unit area. And once you introduce something like atmosphere, then that other second plot on the lower right, the irradiance versus wavelength, it's different. It's no longer a smooth black body spectrum. There's going to be different regions where there's absorption features. And that's from different gases in the atmosphere, water, carbon dioxide, ozone, other things as well. And so although these sketches have satellites, it also applies for UAVs or aerial data. And the reason for this is the light still has to travel through the atmosphere to get to the surface of the Earth. So you're still going to have these absorption features in your data, which you'll probably notice more with hyperspectral, but they'll still be present. Additionally, with some of the atmospheric correction tools that we have, if you don't have reflectance information, they can help you go straight from your raw numbers or raw pixels directly into reflectance. So within ENVI, there's quite a few different methods that we have to correct your data for atmosphere or convert it to reflectance. In just a little bit, I'm actually going to go through Quack, and we'll talk more about that shortly. So once you have your atmospheric correction and you've applied that, the next step to do in some scenarios is basemap registration. So depending on what you want to do, registering to a basemap or registering images to one another can be really important, and it's actually necessary depending on the analysis you want to perform. Some examples of this is say you want to do change detection. If you have time 1 and time 2 and your orthomosaic might be off a little bit, this could be because you don't have the best accuracy on your GPS information. Then registering your images to one another will make sure that the analysis you perform from time 1 and time 2, that each pixel represents the same material in space. And so depending on what you want to do, this step's important. We're going to go through it today anyways. But if you're just looking and want to have an NDVI of your field, it might not be something you need to do. But some scenarios it is. So once you've gone through atmospheric correction and basemap registration, that's when you can start to do some analytics. So the first thing I do just want to point out, we do have lots of spectral indices in ENVI. ENVI ships with 66 total. If you have a different band math expression you want to use, it's super easy to include. they go from vegetation. We also have geology, different vegetation indices as well to, say, look at areas where there's been a wildfire. And part of the reason with all these tools as well, with ENVI, we really worked hard to make sure that you could use all of these analytics without needing to be a remote sensing scientist. So spectral indices are pretty straightforward, but other things like hotspot analysis can be a little more tricky. And so hotspot analysis is something that's new to ENVI. It's in the Precision Agriculture Toolkit. It basically helps you identify regions in your region of interest that have pixels that are above or below an average value. This can be very useful to find variations within your field or something else you're looking at to try to do some sort of like prescriptive mapping, or if you need to, you can find regions where you'll need to apply fertilizer or pesticide or something else to help your plants grow better, just like the other regions as well. So in addition to hotspot analysis, we also have lots of image classification. So with image classification, I'm not going to go through this today, but I just want to mention it. Supervised and unsupervised image classifications are two different workflows that ENVI ships with. This can be really useful, especially for supervised classifications and hyperspectral data. Then you can go through your image, you can find regions of materials that you're looking for, and then you can figure out where they are in the rest of your image. And with hyperspectral data as well, you can also classify your data based off of the end members or unique materials that are within your scene. So the last thing before we jump into our live demo I want to talk about real quick is actually plant counting. So this is also in the Precision Agriculture Toolkit. This really is something that can be like industry changing. If you can programmatically count the number of plants that are in your field, you can have estimates for your yield. You can get your average plant size. You can do some post-processing to try to figure out the plant health. So you have the center and the radius, and you can calculate a spectral index. And then you can go through your pixels and determine the average NDVI or different index within that plant. And so this really has a lot of potential for being something that's a game changer. So this is all I've got for the PowerPoint. We're going to go ahead and jump into the live demo. Give me just a second, and we'll open up ENVI. So this is the image that was shown in the PowerPoints a little bit. This is just an ortho mosaic from ENVI 1 button. I believe it was about 300 images or so that were stitched together. And so this is just the raw data. This is from a sensor called the MicaSense Red Edge. It's got 5 bands. It's blue, green, red edge, and near infrared. And so our first step is we need to get it analysis ready. And so not as exciting, but we'll go through Quack and Basemap registration for this. So for Quack, in my toolbox, I'm just going to type QUAC, and then I'm going to double click on Quick Atmospheric Correction. A dialog is going to appear to choose my input data. I'm going to select OK because I only have one raster open. And then this is the Quack dialog. So Quack is quick because it runs fairly fast, and it's also very easy to use. For the sensor type that predefined with it said it was QuickBird. It's not a QuickBird sensor. So I'm going to switch that to generic or unknown sensor. So at this point, I just have to hit OK. So it's super easy to use. So this will take a minute or two. And while this is running, I just want to explain a few things about Quack itself. So Quack works best when you have a diverse scene. So what does that really mean? You want to have different materials in your scene. Like here we've got roads, a couple different kinds of fields. There's actually some trees. And so it's different materials, and these are all needed so that Quack in the back end can go through and find the unique end members in your image. And so the end members are basically the unique pixels which represent a certain material or the group of stuff that's in your image. And Quack on the back end looks at those end members, and based on their spectra, it will determine the atmospheric correction that needs to be applied. So Quack works well for most cases, but some scenarios it doesn't perform the best. Some of those are if you have a lot of water in your scene, or if you have a lot of clouds. So for both of those cases, you can actually use MB to mask out the clouds or the water, or you can use a different atmospheric correction method called Flash. Flash basically works to model the atmosphere instead of looking at what's in your image to determine the atmospheric correction that needs to be applied. So you see that it ran quickly. It looks pretty much the same as my original image. For R, G, and B, it's not going to change too much, but for other bands it will. Hyperspectral, you'll notice a difference as well. So now that we've got our data converted to reflectance, because we went through Quack and corrected for atmosphere, then we can actually go to Basemap registration. So let me go ahead and open up the Basemap I have. So I'm just going to leave this on top of it for just a minute. This is just NAPE imagery. NAPE is National Airborne Imaging Platform, I believe. And this is just red, green, and blue. So if I reorder my layers here in MB, we can see just like in the PowerPoint, there's regions up towards the top where the roads don't quite line up. There's this kind of dirt area on the right side that doesn't line up as well. Trees in the very bottom left don't line up with the house. And so with our image registration workflow, we can actually correct this and make sure that these pixels represent the actual space that we think they should. So I'm going to open up the image registration workflow. So if I just start typing image registration, it will be the first thing on the list. So with my base image file, I'm going to choose the NAPE basemap. For the warp image file, I'm going to choose the image that I ran through Quack. And then I'm going to go ahead and hit next, and we'll give this just a second. Okay. So at this point, it's our type point generation dialog. So we're going to choose the algorithm that we actually use to find our type points. There's two that are available. There's general, which is cross-correlation, or there's cross-modality, which is mutual information. That cross-modality is just the like sensor spectrum, so that would be registering, say, RGB images to SAR. So in some cases, cross-correlation works better. In other cases, mutual information works better. I ran this already, and I know mutual information is what's going to work better for this situation. So I'm going to hit OK there. Next, I'm going to change my transform from first order polynomial to RST. This is a linear warping that will not allow image shearing. So this just helps preserve pixel integrity. Next, I'm going to go in my advanced tab. I'm going to change my search window from 128 to 200, and that's in pixels. So lastly, I'm going to add some seed type points. So I already did the image registration for this, and so if you have seed type points, it helps speed up the processing. And since this is live, we were going to want this to go a little quicker. So I'm going to go ahead and open up my type points. So once these open, you'll see that some pink little crosshairs have been added to the image. And so if I zoom in, then I can switch back and forth. So this is my base map, and if I switch to my warped image and I zoom out, they're green in my warped image. So there's a couple down here at the bottom as well. We'll give this a second to catch up. So I went around and there's type points all over the place, which is what you want. You want to make sure there's an even distribution. This will make sure that your RST or your warping method actually does a correct job. So now all that I need to do is hit next. Give this just a second. Okay, so this actually registered the images. So once the image registration goes through, I can switch back and forth between my warp and my Basemap. So this is the Basemap, and so if I switch to the warp, then we'll see where the tie points are in each image. This is pretty cool because you can switch back and forth and just do a quick visual check to make sure that the tie points that were generated actually represent the same space, or they are where they should be. You can go through, you can edit tie points if you want, you can manually add them as well. So all I'm going to do at this point is I'm just going to go into my warping. I'm going to change warping method from polynomial to RST, and then I'm going to hit next. So this is actually going to warp the image. And then I can export my tie points if I want, and export my warped image. So I'm just going to export my image. I already have tie points. I don't need to write those out. So we'll just hit finish and let this write to disk. Okay, we'll give this just a second to pop up. Okay, let me take some of my layers out. So at this point, if we look at our images, the trees actually line up. Our roads are actually pretty close to where they should be. So this is now analysis ready. So the first thing we're actually going to go through and do here is hotspot analysis. So like I mentioned in the PowerPoint, the hotspot analysis is part of the Precision Agriculture Toolkit. So before I do that though, I actually need to subset my raster. So I'm going to use the region of interest tool, and I'll talk about why I need to subset in just a minute. So I'm going to open up my region of interest tool, and I'm going to draw a rectangle in the field. And I'm going to right click and choose accept rectangle, and then I'm going to use the subset data from ROIs tool to subset my raster. So I'm going to choose my warped Quack image. I'm going to choose the ROI that I just created, and then I need to select my output file name. So I'll just call this Quack warped subset.dat. And I'll hit OK. So now that this has subset, if I turn off my entire warped image, then we'll see we're just over a field. So now at this point we can go through hotspot analysis. So if I want to open up hotspot analysis, I just type hotspot, and I'll see there's a button for hotspot analysis. So if I double click on that, I have to choose my input file. So during this process, the spectral index is also going to be calculated, and after the hotspot analysis has been performed, we'll actually do a comparison of the two. So I'm going to go ahead and click OK. So within this, there's a couple parameters that we can change. First is the search distance. So this parameter is basically how far you want to look. When you're on a single pixel, you need to look at all of its neighbors and try to determine the average of their values and see how that compares to the global values. And so this is why I subset the raster, because this is all based on statistics. So if I want to compare a region of my field to the rest of the field, then I subset to my field. If I use the entire if I use my entire orthomosaic, then the hotspot analysis isn't going to tell me very much. So with this, I'm just going to choose a search distance of 5. You can use 5 or 10 meters. This is in meters. It will take longer the smaller the pixels you have, because it has to sum more numbers. So next I just have to choose my index. So I'm just going to use a normalized difference vegetation index, which is just the NDVI. And I'm going to choose the option to display my result. So at this point I'm just going to hit OK, and we'll give this just a second to run. And so it ran very quickly. During the image registration, you can choose the output pixel size. I chose to use the Basemap pixel size, which is 0.5 meter, I believe. And so it runs pretty quick. The original pixel size was 13 centimeters, which takes a few seconds longer. So I'm going to go ahead and make 2 views now and pull up the normalized difference vegetation index that I calculated. So I'm also going to link my views together. So to do that, I go to Views, Link Views, and then in this dialog, I'm going to select Link All and press OK. Lastly, I'm just going to put a color table on my spectral index so we can have some context here. I'm going to use the same color table that's used on the hotspot analysis. I'm going to hit OK. So if I start to zoom in here and I actually see I've got my hotspot analysis and my spectral index, you see that they kind of have the same information, but the big difference is that the hotspot analysis gives me regions where the pixel values are lower. So instead of just having, so like if I zoom in up here on this corner, instead of just seeing this stretch of pixel values where the vegetation is not as vigorous, I get an idea of a region where I can actually go through, I could go out in my field, I could give it some more water, give it some fertilizer, see if it has, a bunch of bugs eating my crops or if it's disease. So this is kind of where it starts to get into actual tools that you can use to decide what actions you need to take to correct for what you see in your data. And so another cool thing that is new to Envy, that's actually a little tool that I created, was report generation. So the reason that this is useful too, so if you go through and you find your hotspot, you do your hotspot analysis, or if you calculate your spectral indices, you can make it really easy to share with other people. So we're actually going to go through and I'm going to generate some reports for each of these to show you what they look like. So first I'm going to use the spectral index. So I just called it a spectral index report, and it's just a little button that I added in Envy with IDL. So if I double click on this, it's going to ask me to choose my file. So my input's going to be my warped subset. I'm going to select OK. So then this dialog is going to pop up that's going to have quite a few options for me. Background color is whether if I have a masked image, if I want white or black for the background. Color table, this is a number, so IDL has 74 color tables in it, and they're known by number. 73 is the one that's applied to the spectral index now on the right. So additionally, I can choose some available indices. So I'm just going to choose NDVI. So I'm going to scroll down to Normalized Difference Vegetation Index, but I can choose as many as I want, and a new page will be created for each one. Additionally, I'm going to click this option for creating an RGB page. And then I'm just going to hit OK. And this will take just a second to run. So then a little dialog will pop up. It'll give me the output file path and ask me if I want to display the result. So I'm going to hit OK. And my PDF is going to appear. I'm going to zoom out a little bit so it's easier to see. So in this, since I asked for an RGB image, the first page is just going to be RGB with a little scale bar. And then if I scroll down, the second page is going to be my spectral index. It's going to have a color bar associated with the color table that's been applied. It has a linear 1% stretch as well to help throw out those outliers so you can actually visualize it. And since we also went through the process of getting our data analysis ready, then this NDVI actually will have physical meaning. If you don't go through atmospheric correction and you do an NDVI, it's just going to kind of be relative to your data set. But since we actually did the right steps, went through Quack, we can say for sure, these regions that are dark green are going to be places where the plants are very, very healthy. And then, the red areas is we will know for sure that these plants are, they need some more water or something done to improve their health. So in addition to just being able to use like a report for spectral indices, I also made a report for classified raster. So classified raster is something just that you have gone through and done classification on. And so this is just I called it the classification report. And so I'm going to use this on my hotspot analysis image. This hotspot analysis is actually a classified raster. We can tell by over in the layer manager on the left-hand side of the screen, right by where I clicked, there's kind of this little box that's got little multicolors, and we can see it's got classes. And so based on those two things, we know it's classified. So if I open up my report tool, there's going to be an option for calculating the class areas. So I'm just going to choose my input raster here. I'm going to hit OK, and I'll show you what it does. So we'll need to give this just a second. It takes a little bit longer than Spectral Indices because it has to go through and calculate areas and create some graphs. Similarly, we'll get a little dialog popping up giving us the file path and if we want to open the result. So we'll go ahead and click yes. So this is going to look pretty similar to the report that we just had. It's going to have a little scale bar as well. It'll tell us what we're actually looking at if it's got a band name. And here on the left-hand side, the color bar is going to represent the different classes that we gave it. So there's these large numbers, 23.89, negative 83.95. I believe that's the z-score from the hotspot analysis. I'm not quite sure. It's basically the statistical significance of the actual region that we're looking at. And so anything that's in the kind of green is going to be above average, yellow is going to be about average, and something that's kind of red is going to be below average. So then since I clicked the option to calculate my class areas, if I scroll down a little bit farther, I'm actually going to get a bar plot that's going to give me the area of each class in acres and a key on the right-hand side. So this is really useful as well. If you have an image that you classified yourself, then you can go through and run this utility, and then it will give you the area that each class comprises for the entire scene. Okay, so that's it for hotspot analysis. Next, we're actually going to jump right into plant counting. So I'm going to close this session of MV. And I'm going to bring up another NV. Oops. Give me just 1 second here. I closed the wrong NV. Okay. So for plant counting, NV should pop up in just a few seconds. I'm actually using IDL. And I'll talk a little bit about that while plant counting is running. But basically with IDL, I just want to show that you can run most of the processes within Envy through IDL in sort of a batch or headless fashion. And so I'm just going to go ahead and hit run here. And so since I hit run, a little progress bar is going to pop up for my plant counting. So I wrote a tile iterator to speed this up for this demonstration. We'll give this just a second to run. So with IDL as well, what I'm doing behind the scenes is I'm thresholding the image. And I'll show you what that looks like after this is done. But the reason that I threshold the image is because I want to try to eliminate the number of false positives that are found with the plant counter. So the reason that there's going to be some false positives no matter what is because the plant counter doesn't care if you're looking for a tree or a bush or a shrub or pumpkins or strawberries. If it finds something that looks like it should be vegetation, it's going to count that as vegetation. And so with IDL, you can really get in there, look at your data, manipulate it, and threshold it so that you eliminate the number of false positives that you could have. So this finished running. Let me open up my original raster to show you. Give me just 1 second. So overall, this is the orthomosaic that I'm using to find plants. And so I subset this to just kind of the region where there's the most field. And so I just put, oops, open the wrong layer. So if I open up my subset, you should see there's this kind of blue outline now around the region that I counted plants for. And so before I show what the plants look like, I'm going to talk about my thresholded image. So I just put my thresholded image up. I'm going to give that a color table before zooming in so you can actually see it. So I give it a rainbow color table so it should pop out a lot. And so if I zoom in here pretty close, up on the upper right-hand corner, so you'll see that for the most part, the bright, crazy colors are over the plants. So this is really important because up here in this region, there's actually weeds in between the strawberries. And so like I said, if a pixel looks like it could be a plant, then it might get counted as a plant. And so with IDL, you can go through and get an idea for what your pixel values are, threshold it, which is essentially masking them so that they're not going to be counted as plants when the plant counter runs. And so this really helps eliminate false positives. And so if I scroll around a little bit more, it's mostly up in this region, but it happens in other places as well. So I'm going to zoom out, and I'm going to load up my actual plants that were counted. So for the most part, it does a pretty good job. Occasionally, the plant counter might miss some stuff. I think it's about 95% accuracy. It depends on the crop that you're working with and how much or how well you've thresholded things as well. So like, I mean, if I just zoom in here, you can see there's a couple plants that it missed. There's probably going to be some other regions where it counts 2 or counts an extra. And so this is just pretty cool. We'll go ahead, we'll wait here just a second, and I'm going to flicker this on and off so that you guys can actually see what it looks like. So there's with no plants, and then if I turn the plants on, and so now I'll turn the plants off again, and we'll turn it back on. So it does a pretty good job. One of probably the coolest things about this is even in regions where it's hard to distinguish between plants visually, the plant counter can actually separate them. So the next thing I want to show is actually how you can extend the plant counter. So this isn't something live. I just have some results that I want to pop up. So I'm going to use the same session of Envy. I got to remove all my layers. So in this scenario, I've got some Airbus data. And so I've got blue, green, red, and near infrared. And so this is actually over an orchard. So the last data I was showing was an orthomosaic, which I think the pixel size was about 3 centimeters. And so with really high spatial resolution data, you can get a lot of good information. But you could also use plant counting on something like satellite imagery if you want as well. So what I did, I did plant counting on this. So we'll pull up what the orchard looks like. And so it pretty much gets every tree. Edges are a little goofy sometimes, especially if there's vegetation around there. But within the actual field, we see that every tree has a little circle around it. And so what's really cool is that using IDL, we can actually extend the analysis that we can perform. So for this case, what I did was based off of the tree radius and position, I can actually go through and determine the health or relative health. So that's what I'm displaying here. So basically, this is a visual representation of the distribution of plant healths for this entire area. So it's going to go from dark red to dark green. Dark green is going to be the most above the average health for this field, and dark red is going to be the most below. And so the reason that this is kind of normalized is so if you didn't get your data analysis ready, it's still going to be some useful information to actually see the distribution of health for your plants. So if you can actually go through and find regions of plants that are less vigorous or regions of plants that are more vigorous, then this is really useful. It's also cool to kind of have a visual representation of your plants, I think, as well. It's just kind of nice to look at. It's kind of goofy looking. But yeah, this is just something cool I wanted to show. So, using a little bit of skills with MB and IDL, you can extend your analysis a lot more, and you can get a lot more out of your data. So that's all that I had for the live demo today. I'm going to turn it back over to Dan.
Great, thank you, Zach, for the informative presentation. At this point, Zach will address some of the questions that have come in. As a reminder, you can type questions for Zach using the question area of your GoToWebinar dashboard. All right, so one of them is some of the boundaries of individual photos in the mosaic earlier. That you can notice some of those. Can they be processed to minimize brightness difference?
Yes, you can apply color balancing. You can think of color balancing in two different ways. My stance on it is that I hardly ever do that. I don't use color balancing. So those orthomosaics were produced with MV1 button. You can adjust, you can do actual color balancing, you can do brightness adjustments, you can account for vignetting. They've got two types of color balancing called dodging and profiling. That basically helps your image have a constant brightness across the entire image. So that would be like accounting for vignetting. You can turn those options on. I always leave them off. And part of the reason I do that is because then I know once I get my orthomosaic is that for the most part, it's going to look okay. You might see some lines between the images here and there. But if I look at like a normalized difference vegetation index, I probably won't see much of a difference. And so if I actually, give me just 1 second and I'll bring that up to illustrate. I might need to calculate my spectral index again. So if I pull up this image, and so if I zoom in pretty close to this, so you'll see there's kind of, it almost looks foggy a little bit in the center of the screen. You can kind of see some lines between them. So this is where I don't like to do color balancing at all. But if I just want to, so let me just run a normalized difference vegetation index real quick. So I'm going to click through this pretty fast. Let's let this run real quick. So let me give this a color table. And so once I actually apply a color table to that, since it's normalized, you don't see much of a difference. If I zoom in really close, you can kind of see a line here in the middle of the screen, but for the most part, it's not present. It depends on what analysis you're going to be doing, but for the most part, like if you're just doing something normalized, then that might not be such a big artifact.
Okay, thank you. So is there an option for autocorrelation of the tie points between Basemap image to atmospheric corrected image?
So all of the tie point generation routines can be automated. So I've used them a lot using the MV API. You can go through, it's a couple different steps. It's generate tie points by either cross correlation or mutual information. Then the tie points are actually filtered. I can't remember the names of those tasks. And then it's, I think, image registration task is the last one to actually warp them to one another. I might be wrong about that. But all of that stuff is automated. So you can use it through the GUI, or you can programmatically apply that to all your images.
Okay, is the plant counter available as a tool in Envy, or is it only available through IDL?
So the plant counter is a tool for Envy. It's the Precision Agriculture Toolkit. So if you're interested in trying that out, you'll have to get in touch with your account manager. They can provide you a quote and give you a free trial of that, I think, but you'd have to chat with them.
Do you need to know the altitude to do atmospheric correction for UAV data?
You don't need to. So part of the reason that Quack is really nice and it's very useful is that minimal information from you is needed as input. And this is great because if you don't have reflectance information, you can convert your raw data or digital numbers directly to reflectance. And so I've used that before in many different situations. And so that's why Quack's very useful. You don't have to worry about that, and it's not something you have to account for.
Okay, what is the pixel bit depth of the image used for demo, atmospheric correction, etc.? What is the impact of bit depth on the resulted image?
So the bit depth should stay the same. Well, it'll be when it actually comes out of Quack. So let me back up real quick. So the image that I put into Quack, was a 12-bit depth, about 12-bit depth pixels. So that's from about 0 to 4095. Whereas once it comes out of Quack, it's going to be in units of reflectance. And so with Quack, the reflectance is scaled from 0 to 10,000. The reason for that is a integer is half as many bits as a float. So reflectance is really going to be from 0 to 1. But if you scale that up to be an integer, it saves file size. And so it's 0 to 10,000. If you have lower bit depth, like 8-bit images, Quack should work fine still, but it's just that resolution, that data resolution is just not going to be as good.
Okay, I think that's it for live questions. We do have your other questions, and Zach will reach out to you or someone else. Thank you again for joining us on this webinar. There's a few questions about if the recording will be available, and it will be on harrisgeospatial.com later this week. So you guys will be able to rewatch it. Again, if you have any additional questions, feel free to reach out to us.
All right. Yeah. Thanks everybody for joining us today.
Thank you.